Hello everyone, my name is Dario Cavallaro and I welcome you to this talk about edge disjoint paths in Eulerian digraphs, which is joint work with Kenichi Kawarabayashi and Stefan Kreuzer. So the talk is about the edge disjoint path problem in a specific class of graphs, which are Eulerian directed graphs. Now let's start with talking about disjoint path problems. So you're given a graph G and K terminal pairs, here color-coded and labeled by Si and Ti. And you're asked, well, do there exist paths, disjoint paths that go from Si to Ti? Now, normally you want more restriction on those paths. So for example, you could ask, do I have vertex disjoint paths that connect Si to Ti? That is, paths that connect S1 to T1, S2 to T2, and S3 to T3 without sharing common vertices. And in this specific instance, the answer is no. You cannot do this because any path from S3 to T3 would need to intersect path from S1 to T1 or S2 to T2 in a vertex. So you could change the question and ask, well, do there exist edge disjoint paths? In that case, they're allowed to share common vertices, but they're not allowed to share common edges. And now this instance would be a yes instance because you can find 3 edge disjoint paths, routing Si to Ti. And of course, we can generalize this to directed graphs, where you ask for directed paths between Si and Ti. And this is the problem that we will look at, but we will look at it in a different setting, that is the demand graph setting. So instead of being given K terminal pairs, we are given K back edges, which are basically encoded in a graph, demand graph D, that is every back edge goes from Ti to Si, telling us we want to route from Si to Ti. And the reason why we look at it this way is because it helps with inductive reasoning on Eulerian digraphs. So disjoint path problems have been studied for decades, and in the early 2000s, Robertson and Seymour presented a major breakthrough result. They proved that the K-vertex and edge disjoint path problems can be solved in polynomial time for every fixed K on undirected graphs. That is, the problem is fixed parameter tractable with respect to K. And at the heart of the correctness proof of the algorithm lies the graph minus structure theorem, a deep result about the structural properties of undirected graphs. Now, people tried to analyze the directed versions of the vertex and edge disjoint path problems, and it turned out that, well, in the directed setting, things break down really quickly. That is, the directed 2 vertex and edge disjoint path problems are already known to be NP complete. And so we think unless P equals NP, that there is no polynomial time algorithm solving this problem. Then people started to look at, well, what structure can help us with routing paths disjointly in a directed setting, and well, it turns out that even not admitting cycles, directed cycles, so being directed acyclic graphs, does not really help with routing. That is, it was proved that, well, the directed K-edge disjoint path problem is still hard even on planar acyclic directed graphs. Well, fortunately, there have been some positive results too. That is, for the vertex disjoint path problem, actually planarity does help, and the directed K vertex disjoint path problem on planar directed graphs is actually fixed parameter tractable with respect to K. So this also shows a little bit the difference between the edge disjoint and the vertex disjoint path problems. Now, one can ask, what is the structure that helps with routing edge disjoint paths in the directed setting? And it turns out that Eulerian digraphs help doing so. So what are Eulerian digraphs? Well, a directed graph is called Eulerian if at every vertex the in-degree and the out-degree are the same. That is, the number of edges that goes into a vertex equals the number of edges that go out of a vertex. And well, for Eulerian digraphs, there have been early results about routing paths edge disjointly. So if you're given a graph G plus D, where D is the demand graph and the graph is G plus D is Eulerian, then the 2 edge disjoint path problems is actually polynomial time solvable. And well, soon after that, it was proved that this holds true for K equals 3, so the 3 edge disjoint path problem is also polynomial time solvable when G plus D is Eulerian. And then, well, the same authors went on analyzing different variants of edge disjoint paths in variants of Eulerian digraphs, and well, they proved that for several cases and K lesser equal 3, that the edge disjoint path problem remains polynomial time solvable on some variants of Eulerian digraphs. And now then the question typically coming to mind is, well, what happens if we have more paths? If we're looking for more than just 3 paths, so what happens with K bigger than 3? And that's actually the question of the paper, and that's what we looked at. So we have proved that, well, if you're given some integer K and some instance G plus D being Eulerian, then, well, actually the problem is fixed parameter tractable with respect to K. That is, for every fixed K, you can solve the instance in polynomial time. Now, the algorithm behind this theorem is rather easy, and actually it is well known. because it is very similar to the undirected case. So let's recap the undirected algorithm given by Robertson and Seymour. And it goes a little bit like this. So you're given an undirected graph G and k pairs of vertices, SITI, that you want to connect. Then there's some huge function, just think about some huge function, and 2 steps. So step 1 is, well, either your tree width is bounded by that function of k, in which case, well, the tree width is bounded in k, and you can solve the problem by dynamic programming using Cosel's theorem, for example. So let's assume it is bigger than k. Then, well, what they do is they locate a vertex in the graph that you can throw away. It's irrelevant to your problem. So basically, you reduce your graph in every step. As long as your tree width is big, you start reducing your graph, deleting vertices, kind of a reduction, until your graph is so small that the tree width of the graph is small, and then you're back in step 1, and you use Cosel's theorem. So the problem is then, how do you find this vertex that is irrelevant to your instance? Well, to do that, you have to think, well, what happens if the tree width is large, right? Well, one way that the tree width is large is you have a big clique in your graph. Or rather a clique minor, but let's not go into the details here. And well, what does a clique do? Well, a clique actually helps you with routing. So think about this clique and ask yourself, well, does my solution use this clique? If I have paths that in my graph and they don't use vertices of this clique, well, then the vertices are irrelevant, right? So let's assume they use the clique. Then how do they use the clique? Well, if the path enters the clique and it leaves the clique again at some point, and all your paths do that, well, actually then you can just route them directly in the clique. And if the clique is huge, then there's some vertex that you don't need in rerouting your solution. So if the clique is huge, then there's some vertex that's not needed to route your solution. And that's basically an irrelevant vertex. And you continue deleting such vertices until there's no big clique minor left. And in that case, they prove that, well, if you do not have a huge clique minor, there is some structure theorem, which is a pretty hard and long proof, but in the end, you have some bookkeeping about your graph where you embed it on some structure, and when you do that, then you can prove that, well, you find another vertex somewhere on that structure that you can locate, which is irrelevant to the instance, and you continue deleting until your graph has small tree width. Okay, so what happens in the directed setting? Let's just try and do that too. So we get given a directed Eulerian graph in a setting, G plus D being Eulerian, and where we can reduce our attention to maximum degree 4, right? This is just some easy reduction. Let's not care about this too much, but it's just we can reduce the degree of the graph to 4. Then, okay, let's assume we have some huge function, and we know that the tree width is smaller than that function of the graph. But then again, we too can use Cosel's theorem, right? So we are done. Okay, so now the tree width is big. What now? Well, the thing is, we cannot delete a vertex. Because if we delete the vertex, then the graph is not Eulerian anymore. So you have to think about what can we delete that doesn't influence the Eulerianness of the graph. The thing is, we can delete cycles in an Eulerian graph, the edges of cycles, keeping it Eulerian. And so what we want to find is, well, can we find a cycle quickly so that deleting that cycle does not change our instance? Can we find an irrelevant cycle? Actually, we can. The question is just how. Right, let's think what happened in the undirected setting, right? We had some clique, something that helps us with routing, so that, well, you don't need everything in that structure in the clique to route. There was some vertex that was irrelevant. So the question is, well, what structure helps with routing edge disjoint paths? And the answer is a router. So we just called it a router because it helps with routing, right? Now, what is a router? Well, a router is just a set of cycles that are pairwise edge disjoint and pairwise intersecting. Now, there's one notable difference to the undirected setting, cliques, where cliques are highly non-planar, but routers, they may be planar, right? And so why do routers really help with routing? Well, assume you have a large router, right? And then, well, if we have a solution that would not use this router, then somehow the cycles would be irrelevant anyway. So we would have to ask, well, how do solutions use this router, right? And that comes back to the question, well, how can we get into the router and back out? And do that simultaneously. And this is a question that in the general directed setting is not easy to answer. But in the Eulerian setting, we can answer it. And actually, there's an algorithm by Frank that lets us test it. So we can use an algorithm, adapt it to our case, and then ask, well, can our solution get into the router and back out and use it? And if it can, then we can do it in such a way that there's at least one cycle left that we didn't use. We can reroute it to not use this cycle. And so if there is a solution using a router, then it does not use this cycle, and that's an irrelevant cycle. So if we have a large router, then we're done, right? If you have a large router, we can locate a cycle that we can delete. So the question is, what happens if there is no large router? And well, remember that in the undirected setting, they started to do some bookkeeping and had the structure theorem. So is there a structure theorem for directed graphs? And the thing is, directed graphs, they are built different. There is no directed structure theorem, at least no known one. But the question is there a structure theorem for Eulerian digraphs? And the answer is yes, there is. And the thing is that if the tree width of your graph is very high and you exclude a large router, you have no large router, then it turns out that you have a large swirl. And a K-swirl is just a planar graph consisting of 2 K cycles, where the cycles are in alternating order, and your graph contains some large structure where the structure is a cylindrical K-wall. Now, if you don't know about K-walls, just think about the undirected graph containing a large undirected grid. And if you don't know about grids, then just think about the graph looking exactly like in this picture. And more importantly, the graph is not only planar, it is Eulerian embedded, which is exactly every vertex looks as on the right picture. That is, every in edge is followed by an out edge, then there is an in edge again, then there's an out edge again. Now, vertices are degree 4, so they look exactly this way, and that is, you cannot cross paths in a vertex. So, as I mentioned before, you get the following theorem. If your tree width is larger than some huge function, then either you get a K router, which helps you already finding a relevant cycle in that router, or you get a large swirl. Now we can prove more than that. We can prove that the swirl is actually flat. Now what that means is just inside the swirl, not only the swirl itself is Euler embedded, but basically everything attached inside is Euler embedded. That is, you cannot cross 2 paths in a flat swirl, right? And this is the kind of planarity that we want. We don't only want the graph to be planar, we want to ensure that if it is embedded, there's no way to cross paths inside the embedded part. And so, having proved this result, you have gathered almost all the tools that you need to prove the structure theorem. Now, the easiest way to prove the structure theorem from here is to just find out that someone else did before you, and that is, Johnson proved a version of the Eulerian structure theorem in his dissertation. Now, unfortunately, the work has never been published, but still, we thought that, well, he proved a version that suits us and that is enough for us, and we have proved all the details that we need so far, and we can extend the proof to full proof. So from here on, we just used his theorem because it suited our needs. Now, in a nutshell, the theorem reads as follows. So you're given a graph G that is Eulerian, and it does not immerse a large router, say a T router. Then there exists some surface of bounded genus, bounded in T, such that you can almost completely embed your graph in that surface, and more than just embed, you can Eulerian embed it. That is, you cannot cross at any vertex. You cannot cross paths at any vertex. And in addition to that, you have a large disk in your surface that embeds a huge swirl. And then there is some edges that you simply cannot embed. You just don't embed them, but there's not too many of them. And then there's some regions called vortices that are also not Eulerian embeddable, so they may have vertices that admit you to cross, allow you to cross paths, or they may have non-planarity, but they are somewhat tamed. They are of bounded depth. That is, you don't have a lot of paths going from one side to the other side. And so, in a sense, you have a structure theorem similar to the undirected one. Remember, in their proof, Robertson and Seymour proved that, well, if you have the undirected structure, if you have the structure theorem, then you can use that bookkeeping, the structure theorem, in a sense, to locate an irrelevant vertex. Now, we will do the same. Using the structure theorem, we will locate an irrelevant cycle. So, the question is, where is the irrelevant cycle, right? And how do you locate it? And well, the theorem is as follows. If you have this nice embedding, and the large swirl embedded in this large disk, then actually, if the swirl is large enough, then the inner cycle of the swirl is irrelevant to your instance. And the proof of this is basically 2 steps. So the first step is you forget about the stuff that you could not really embed. Forget about the vortices and the edges, and you think about the graph being completely embedded in your surface. Then you can look at your swirl and ask, well, how can my paths interact with this swirl? And now this crucially uses the Eulerianness. This is the analysis is not the same in the general directed setting, and we need Eulerianness here to prove some structure on the paths behaving the way they behave inside the swirl, to actually prove that you can pull them apart and they don't go too deep inside the swirl, they don't interact with it too much, so that, well, the middle cycle becomes free and you can actually delete it, you do not need it. So we can reroute inside the swirl. And now there's the question, okay, well, what happens if you still have vortices? Now the idea is to bound the number of interactions that our solution can have with vortices. So to be in a sense tame how our solution interacts with the vortex and be like, okay, cannot use the vortex too much, it cannot use it to cross paths too much, and then this roughly doesn't change the fact that the cycle in the middle of this swirl is irrelevant. And now how you go about proving this, again, really uses the Eulerianness. So you have to analyze the structure of the vortex. So think about a path interacting with the vortex a lot. Now what you want to prove is that it doesn't have to do this. You can reroute it so that it doesn't interact with it too much, and it just goes in, like, say, once in and once out. And to do that, you need some structure and arguments how to reroute inside. And that is, here, Eulerianness is really crucial. Eulerianness allows us to structure the vortex in such a way that we get neat paths going from the left, going through the vortex from one side to the other and back. And that way, we are able to reroute the red wiggly path inside the vortex to some neat path that, let's say, interacts with it just a few times. And that way we bound the number of interactions of every single solution with every single vortex, and then we can use that to reduce the problem to the case where the whole graph was embedded in the whole surface. And so, to recap, well, what we do is basically, if it has low tree width, right, then everything works as always. You just do dynamic programming. If it has high tree width, then you want to locate an irrelevant cycle. And either you have a large router, in which case you find an irrelevant cycle, or you don't have a large router, in which case you have a large swirl and a nice embedding and a structure theorem, and where again you found an irrelevant cycle in the middle of your swirl. So you find these cycles, you delete these cycles, you reduce your instance until you have low tree width, and then you're done by dynamic programming. This sounds easy, and the thing is, there is some details that we have hidden here. The demand graph edges, you will not be able to embed those, and it is needed that you don't embed those, and then you have some tricky details, but that's up to you if you want to read it or not. Well, for that, thanks everyone for listening in, and have a great time.